Hello, everyone. Welcome back. This is the next half of the session. We will have the presentation delivered by Professor John Ogren. Again, so please allow me to introduce Professor John Ogren. Although I know many of you, almost every of you know him well, we still have some people join the cover meeting for the first time. So John holds a PhD from the KTH, Royal Institute of Technology in Stockholm, Sweden, 1981. And he was appointed a full professor in physical metallurgy at the same time, same university, 1991. After his PhD, he has been stayed at Men's Labs in US, in Boston, I believe, probably also together with Larry Kaufman at that time. And then he also stayed in Max Planck Institute in Düsseldorf for periods of time. He was the head of the Department of Material Science and Engineering at KTH from 1993 to 1997, and the chairman of PhD studied in Mechanical and Material Science Engineering from 1993 to 2003. He was a member of the KTH faculty board from 2003 to 2006 and has launched and been the director of two excellent centers. One is BRIE and the other one is a Hero M Center. By the way, I got my PhD degree from KTH through the Hero M Center funding. And he is one of the developers of the software Samokek and the Dicture, and one of the founding fathers of the company Samokek Software AB, and is the chairman of the directory board since 2001. He is a member of the Integrated Computational Materials Engineering ICME committee of the TMS since 2009. He has been instrumental in introducing the concept of the materials genome. John is a member of the Royal Swedish Academy of Engineering Sciences and a fellow of ASM since 2011. He was elected as a member of US National Academy of Engineering in 2018. John has been the main supervisor for at least 28 graduate PhD, which are now active in academia and industry in Sweden and worldwide. And probably you already know that the play was studied with John as a main supervisor. Without saying too much more, I think we can directly go to enjoy his presentation. He has a video recording, and please allow me to share. So, I think this should be the one. Okay.
Thank you very much. In this presentation, I will discuss CALPHAD development over the last decade, and in particular how it relates to the materials genome.
So what happened? I cannot hear you, but the video was played
by President Obama 10 years ago. And thank you very much. In this presentation, I will discuss CALPHAD development over the last decade, and in particular how it relates to the materials genome. I will concentrate on some basic ideas in CALPHAD which fits very well to the materials genome. The Materials Genome Initiative was presented by President Obama 10 years ago, and it concerns the development of fundamental databases and tools which could enable the reduction of the time to develop and deploy new materials with a factor of 50% or more. As a background, one may mention a report from the National Research Council 2004, where one was worried about the fact that the academic value system in physical sciences did not really appreciate the creation of engineering databases. And that was very much in contrast with life sciences, where one had the Human Genome Project, and that is actually the greatest engineering database in history. So one would like to have a fundamental database initiative also in engineering sciences, and such an initiative could support the computational materials engineering and the design of new materials. So if we now look at the framework for materials and process design, we have the goal of the Materials Genome Initiative, and here on this side we have the Materials Genome, which is models and databases. And on this side we have ICME, Integrated Computational Materials Engineering, which is actually the integration of materials information systems. And down here we have materials design, which is a method to design new materials and new processes. So, a genome is a set of information encoded in the language of DNA that serves as a blueprint for an organism's growth and development. The word genome, when applied in non-biological contexts, connotes a fundamental building block toward a larger purpose. We know a lot about materials, but the knowledge is complex because structure and properties are complex. There are many alloy elements, many different crystal structures, that is, many phases. We have interfaces between those phases, and there is a hierarchic structure ranging from atomic up to macro scale. It is dynamic because structure and properties change during time, during the synthesis and processing of the material, during the use, and after the use when we want to recycle the material. And there are many different types of information. We have experiments revealed in phase diagrams, transformation diagrams, etc. There is theory, ab initio DFT, CALPHAD, and so on. There are empirical rules and guesses, and there is other information as well. So here is the content of my presentation. I have already given you the introduction, and then I will go to the knowledge challenge, and I will discuss how CALPHAD is a way of processing data, and then CALPHAD extended to other properties, example of industrial use, and CALPHAD far beyond equilibrium, and finally some issues in CALPHAD where there is room for improvement. So there is a knowledge challenge. How can knowledge of materials, which is so complex, be integrated into a single framework to allow extraction of useful information? Or in other words, how can a materials genome be constructed? We have a number of examples of classical knowledge in material science and engineering. We have phase diagrams, stable or metastable, various types of sections and projections in multi-component systems, different types of quantities on the axis, and we have thermochemistry, heat capacities, heats of transformations, chemical activities, voltage in batteries, and driving forces for non-equilibrium states, and much more. And then there are also the thermophysical properties, thermal expansion, bulk modulus, etc. One should realize that there are at least 3 different levels of data. We have the raw data, and such raw data may be processed. So we get processed data, which is now much more refined data. And such refined data can be used in various types of simulations, and we get some results of those simulations. So the raw data, which we also call the proto-data, is a non-processed data. Those are experimental measurements, although they are usually processed to some extent. For example, an electric signal is transformed to a temperature. We have ab initio calculations. They are based on some approximation and some computational methods. And then we have various type of estimates based on rule of thumbs. They are based on general experience. Sometimes there is a less clear origin. Now, this constitutes proto-data, the raw data. So the raw data is then processed, and we get the processed data. So one type of processed data is average values. And one example is hand-drawn phase diagrams to fit experimental points. One other type of processing is regression analysis, and then the result is a line characterized by some values. Another way is to use neural networks or machine learning, and then the processed data is a trained network. And finally, we can fit to a physical model, and then the result is a definition of the model and the values of its parameters, and that is where we have CALPHAD. The processed data can then be used in a simulation, for example, a heat flow simulation, solidification, diffusion, phase field simulations. So CALPHAD is a way of processing data. CALPHAD, as you know, was initially developed to represent experimental information on thermochemistry and phase diagrams. And this is actually a massive reduction in data, so a large number of experimental data of different kind is represented by a few parameters. It is a consistency check. It sorts out information that is probably wrong. It is a structured way of storing data for easy retrieval when needed. And it allows extrapolation from simple materials to complex materials and direct industrial use of the information. So I will claim that CALPHAD is the first materials genome because it is the most efficient way of integrating various pieces of information of quite different character into a coherent and useful form. It is extendable far beyond the traditional thermochemistry, and it is increasingly being used outside the traditional CALPHAD community. So it is actually a major enabling technology in material science and engineering. The CALPHAD method can thus be regarded as a role model for materials genomic databases. It is based on the rigorous and self-consistent thermodynamic analysis. A CALPHAD database consists of highly processed data combined with models. The type of models used based on a hierarchy, unary, binary, ternary, gives a logical building blocks to represent properties in a genomic language. So the materials genome in CALPHAD. Well, Larry Kaufman and I, we argued that the materials genome in analog to the biological genomes should be defined as a set of information databases allowing prediction of a material structure as well as its response to processing and usage conditions. So the main vision behind CALPHAD, and that is, of course, rigorous science. So if we know the Gibbs energy of system as a function of pressure, temperature, and composition, and some internal variables, we can calculate a lot of properties. For example, we may calculate the state of equilibrium for given conditions. We can calculate different types of phase diagrams. We can calculate thermochemical and thermophysical properties, and also other quantities of interest, for example, driving forces for reactions and transformation if the system is not at equilibrium, and that can be useful in phase field simulations. We can calculate properties of metastable states and metastable phase diagrams. It is interesting to see what Einstein said about thermodynamics. He said, "It is the only physical theory of universal content which I am convinced that within the framework of applicability of its basic concepts will never be overthrown." More recently, Homer Simpson said, "Lisa, in this house we obey the laws of thermodynamics." Here I would like to make an important remark on thermodynamics. Thermodynamics does not only apply at equilibrium, which is a condition where nothing more can change, because measurements can be performed sometimes quite far outside equilibrium, and they can be extrapolated further into the non-equilibrium regime. Thus, thermodynamics applies considerably outside equilibrium. But how far would it apply? Well, we will demonstrate that thermodynamics may be applied as far as needed to solve certain problems. There are some aspects of CALPHAD which you must realize. Although it is based on the rigorous laws of thermodynamics, it makes use of the Gibbs energy or some other thermodynamic state function. But the Gibbs energy of the system is never known exactly, neither the other suitable thermodynamic state function. It has to be determined as well as possible, consistent with available experimental and theoretical information. Thus, we leave the world of rigorous science and enter the world of approximations. So, what model to represent different types of information? How well can we represent experimental data? And of course, we can use fundamental data based on DFT if we do not have any experimental data. But you should realize that DFT is an approximation itself. It might be the best approximation we have. And in fact, there are many sub-approximations within DFT, and so on. So we have here reality, very complex. And from reality, we extract the protodata, experimental measurements, ab initio calculations, general experience, educated guesses, non-educated guesses, and then we use models. And in those models there are parameters. And in each model we choose the parameters that represent the protodata as well as possible. And a model combined with its parameters then give us a genomic database, which is a high-quality database. And here you should also realize that individual parameters usually have no physical meaning, at least no simple physical meaning. Only when all of them are combined with their model, they have a meaning. Also, it is important to note that the CALPHAD model can have any level of sophistication, and it can account for crystallographic structure, that is vibrations, chemical order and disorder, and other phenomena like magnetic order and disorder. Different phases in the same material can be represented by different models and require different types of parameters. Quantities which are experimentally unknown or uncertain or show a large scatter, they may be estimated by ab initio methods. So CALPHAD. Well, we distinguish between the different generations of CALPHAD. So the first one appeared in the late 1960s, and I would say, really took off with a book by Kaufman and Bernstein, Computer Calculation of Phase Diagrams. And Kaufman and Bernstein, they used simple regular solution models and polynomials for temperature dependencies. And the second generation appeared some 20 years later, when one started to accept more advanced models. There were new computer codes like FACT, ThermoCalc, empty data, and a little bit later PANDAT and FactSage. And very important, there was an internationally accepted descriptions of the pure elements, which was published by Dinsdale, 1991. And this was approximately valued down to 300K. And there was also extension to diffusion kinetics, and the Dictra software was introduced. So the third generation, where we are now, it is characterized by physically based models allowing extrapolation down to 0 Kelvin, new advanced magnetic models, and models for highly supercooled liquids, that is glassy materials. So let's look about CALPHAD extended to other properties. I already mentioned extension to diffusion, but there are also extensions to viscosity, to interfacial properties, for example, mobilities, energies of interfaces, stacking fault energy, extension to elastic constant, anisotropic behavior, extension to mechanical properties like strength, ductility, toughness, fatigue, and to electromagnetic properties like optical, electronic, and magnetic, and so on. So CALPHAD extended to diffusion. Well, in that case, gradients of thermodynamic potentials serve as a driving force for diffusion, and we can write it in this simple way. The diffusive flux is equal to minus some coefficient times a gradient in the thermodynamic potential. And actually, those quantities are vectors and matrices. So this J is a vector containing the flux of number 1, number 2, and so on. And then this L is a matrix, usually called the phenomenological matrix. And this quantity is a gradient in thermodynamic potential. And here you can see for the transported quantities, what the corresponding thermodynamic potential is. So for heat, it is 1 over temperature, and for diffusion of atoms or species, it's their chemical potential divided with temperature, and so on. So if we have isobarothermal diffusion, we can write the flux as a diffusion coefficient matrix times this gradient in composition, because that would be Fick's first law. But we know that we could also write it this way. So by making identification, we find that the diffusivity is a molar volume times a phenomenological matrix times a matrix which is only a thermodynamic quantity, and that is called the thermodynamic factor, and it can be obtained from CALPHAD analysis. So a CALPHAD type of approach was suggested for analysis of information of diffusion kinetics by Anderson and Ogren 92. And in fact, that allowed a systematic representation of the kinetic behavior of multi-component alloy systems. And in the 1990s, DICTA was developed for a numerical solution of the multi-component diffusion problems. So when we map the diffusion genome, we choose a model for diffusion, and usually we choose a vacancy model, which means that diffusion occurs by atoms jumping to a neighboring vacant site. And then we fit all parameters in the model by a CALPHAD type of assessment to available data on diffusion. And we have experimental data, which is tracer diffusion, diffusion couples, diffusion multiples, and so on. And there is theoretical data, DFT calculation of activation barriers. We have some input from statistical mechanics, atomistic simulations, and so on. So here is one example. It is a database for nickel-based alloys developed by Campbell and co-workers at NIST. And this shows a joint between two nickel-based alloys. And you can see that there are many alloying elements here. And they used a simple substitutional model for this alloy. This is in FCC phase. So we show here the concentration profiles of the different alloy elements. And here is the position of the initial joint. The situation is summarized in this view graph from Kettner and Campbell 2009. On this side, we have phase equilibrium thermodynamics, and on this side, diffusion. And we have the proto-data, various kind of experiments, and then we have the models, and we have theory, typical DFT, and then we extract the parameters which give us a thermodynamic description and put them in a thermodynamic database, and we can then calculate various phase diagrams and phase equilibria. In diffusion, we have the proto-data, which are various kind of diffusion experiments, and we have theory, atomistic calculations, and again, we extract the parameters, which are typically mobilities, and put in a diffusion mobility database. And observe that here we also need a thermodynamic factor for calculating diffusion coefficients. And then we can do various kind of applications. So we have this joint between the two nickel-based alloys, and we can do other kind of applications. So here is a remark on the Matthias genomic database for diffusion. Well, in an advanced genomic database for diffusion, you need, of course, a diffusion model and an accompanying thermodynamic model, because the thermodynamics enter into the driving forces. And we have mobilities, which are the parameters we evaluate. And it is easy then to include other effects like Manning correlations. We have heat of transport to treat the effect of temperature gradients. We would have the charge of transport for electric gradients. We have strain volumes for treating diffusion induced by stresses. So it becomes rather complex. We also need what I would call lattice mobilities, which would correspond to the lattice stabilities in classical CALPHAD. And here the workshops at NIST, initiated by Campbell and co-workers, have been very important. So let's now consider an example of the industrial use of materials genome and CALPHAD. This example concerns modeling of gradient sintering of cemented carbides for metal cutting and drilling. And metal cutting and drilling, well, metal cutting are typically done with this kind of tools. And this is a collaboration between three Swedish cemented carbide producers and KTH, and the work is done within the center herein. So the goal here is to produce a new class of cobalt-free cemented carbides. Cobalt will be replaced then by other phases. The reason is that cobalt has a number of issues. So here is the cemented carbide, the microstructure of a cemented carbide. This is a rather coarse cemented carbide, and those are very hard materials and very resistant materials, and they are made by powder metallurgy and liquid phase sintering. And here is a microstructure. The phase here, the light gray phase, is the binder phase, the cobalt in the classical cemented carbide. And the dark gray phase here is the hard phase, the tungsten carbide. And then usually there are also secondary hard phases with FCC structure of various cubic carbides or carbonitrides. So those tools are, for various reasons, they are made with a structure gradient. And they are, after having this structure gradient, they are coated, and that gives you rather tough material, well, at least a tough surface zone. And it turns out that if you do the sintering under denitriding conditions, you get a tougher surface where there are no cubic carbides and there are higher content of the cobalt binder phase. And what would you like to do? Well, you would like to predict the gradient formation. Now, this gradient formation occurs during the liquid phase sintering. The problem is that diffusion in liquid is not very well described. Here is a type of microstructure we are talking about. We have a surface coating, and here we have the gradient zone, and this is now treated for various times. So in this layer, there are no cubic carbonitrides. Here, on the other hand, we have the dark phases here, or the cubic carbonitrides. So this is a gradient zone. So here is typically what it looked like. And you can see clearly here the gradient zone. So why do those gradient forms when you sinter in a denitriding atmosphere? Well, what happens is that nitrogen diffuses out of the material because the atmosphere is denitriding. Now there is a strong attraction between nitrogen and titanium. So when nitrogen diffuses out, titanium diffuses inwards, where there still is a high nitrogen content. And that means that this reaction can be controlled either by nitrogen diffusion outwards or inwards titanium diffusion. So how did we estimate the diffusivities in the liquid binder phase? Well, we used molecular dynamics, ab initio molecular dynamics, and considered the various diffusing elements in the liquid phase. And then those were used to evaluate mobilities, and we could then simulate the gradient formation with the Dictra code. And this was work by Martin Wahlbro a couple of years ago. And here is shown the diffusion coefficient for various alloying elements as a function of temperature. Here is shown the result of the Dictra simulations. And on this side, we have the number of moles of the different phases as a function of distance from the surface. And here is experimentally observed gradient zone. You can see it here. And this is a cubic carbon nitride phase. There is a maximum here, and then it goes down to 0, and you have the gradient zone. And here is for some other conditions, and you can see that there is a reasonable agreement. So now let's look at the application of CALPHAD far beyond equilibrium. So here we look at the prediction of glass formation. It is known that when a liquid is cooled, it solidifies into glass if we can avoid crystallization. And that means that we can use the precipitation models to predict the fraction of crystals for a given cooling rate in a liquid. And here is one example where we see the volume fraction of the different solid phases, crystalline phases, when we cool a liquid of this ternary iron niobium boron alloy. And the cooling rate is here 1,000 degrees per second. And we can see that we get very low fractions of the FCC and the BCC phase. So it is less than 1% of the BCC phase. And the other two phases which can form here shows so low content that they will not form in practice. So it means that when this alloy is cooled with 1,000 degrees per second, we will essentially bypass the crystallization. Only very tiny amounts of BCC and FCC will form. So to predict the crystallization rate, we need thermodynamic properties of the undercooled liquid, the different crystalline phases, and the interfaces between the crystal and liquid, and that is the interfacial energies. We also need the kinetic properties of the undercooled liquid, so the diffusion mobilities and the viscosity. So the properties of the undercooled liquid, we can use experimental information on the heat capacity, which is proportional to the second order derivative with respect to temperature of the Gibbs energy. And we must combine that with a reasonable model to obtain the Gibbs energy of a highly undercooled liquid. And we see from the experimental information that the heat capacity increases when we cool the liquid without crystallization. when we extrapolate the Gibbs energies using the experimental heat capacities, Gibbs energy as a function of temperature will no longer be straight lines. They will be curved lines, which means that they may intersect. The Gibbs energy of the liquid and the Gibbs energy of the solid may intersect several times. So it is illustrated here where we have the normal melting point. So here the Gibbs energy of the solid is higher than that of the liquid, and the liquid is more stable. But then we find that there is an intersection also at low temperatures, which would mean that the solid would melt at this temperature, because the solid now has a lower Gibbs energy. And in a similar way, there is an intersection at high temperatures, which means that the melt would then solidify at high temperatures. And those two predictions are, of course, absurd, and they are just based on a bad extrapolation of the experimental information. So a reasonable model for the undercooled liquid is based on the following physical picture. We consider two states of motion in the simple liquid. So the atoms, or sometimes molecules, they perform the two kinds of motion: translational, like in a gas, and vibrational, like in a crystal. And it is actually surprising how large fraction of the atoms that are vibrating in a small cage confined by their neighbors, even at the melting point of the stable crystalline phase. As temperature is lower, the fraction of atoms with the vibration motion increases, and this is represented by a decrease in the entropy, that is, an ordering. And from statistical mechanics argument, we can find that the difference between translational and vibrational motion is K Boltzmann per atom, the difference in entropy. So this led to the two-state model, and it gives the same thermodynamics as the Schottky two-level model, and it allows a physically realistic extrapolation of the liquid properties to low temperature, and thus a realistic calculation of the driving force for crystallization. So in fact, we can derive this kind of expression for the fraction of atoms with translational motion. And here is an example now for pure gold. And it shows the heat capacity in the FCC phase, and here is in the liquid, which is undercooled. Here the symbols are experimental, and here are the behavior predicted by the model. So we expect that the entropy of the liquid will decrease until slow kinetics put an end to it and we reach a glass transition. And here are the corresponding variations in the Gibbs energy and the entropy. And here is a fraction of atoms having the translational motion. And you can see that it is typically close to the melting point. It may be around 0.5 or something. Well, this approach was used by Mao and co-workers to consider glass formation in the iron-boron binary system. And they use a TC Prisma precipitation model. They calculated the critical cooling rate to avoid crystallization for various composition of boron. And you can see that here at low boron content, the crystallization occurs by FCC or BCC phase forming, whereas at the higher boron contents, crystallization occurs by formation of Fe2 boron. And there is a minimum in critical cooling rate at this point, which is close to the eutectic composition, but not exactly. So this can be, so here is where we would expect the best glass forming region, which is in agreement with experimental observations. And now finally, we come to some issues in CALPHAD where there is room for improvement. First, one should realize that the present CALPHAD databases represent huge investments. Nevertheless, databases need to be revised continuously in order to remove various artifacts caused by bad choice of equations to represent properties. Data need to be underpinned by better physical models, and that leads to the third generation of CALPHAD. A very important thing is to estimate the uncertainty of a CALPHAD-based calculation, and here the use of Bayesian statistics and machine learning seems very promising. And that ends my talk. Thank you very much.
Again, thank you very much. So that's a very nice and interesting talk as always. And I see there are a couple of discussion already in the Q&A session. We encourage people to asking questions through the Q&A, and we can also promote some people to the panelists to have a discussion. I think you may be able to take over from now.
Okay, so the suggestion I have is we have limited time for the Q&A in Zoom. Of course, we can always elongate it a little bit. My suggestion is you and me and also Scott, we can read one question, one by one, and then have the speakers to answer. Okay, so the first one I saw is like Ursula, you asked quite several questions. Let me promote you as the panelist. Let me see. What's happening?
John and Philip, if you don't mind, you can also turn on your camera, I guess.
Oh, okay, Ursula, I see you. Let me see. All right, Ursula, you can share your camera now, and you can ask your question.
Well, I ask my questions. The one thing is whenever I'm dealing with the volume is the question, and John answered it already in the Q&A. We are moving towards an equation of state. But mostly when you do the classical CALPHAD, you treat it as a non-thermodynamic variable. So,
yeah. So I think in most cases, the pressure variation, the variation in molar volume due to pressure is not so important. But of course, when you go to high pressures, like in geological system or in special processing, then it becomes important. And then you need to consider also the pressure dependence. And as you know, it is based on various equations of state, which you can turn into Gibbs energy functions in some cases, or some cases you have Helmholtz energy functions. But in most practical cases, it is not so important. So then you could do well with just temperature dependent molar volumes.
well, the main reason where my question was coming from, and you actually addressed that in your last slides, when you learn something and you want to expand, it may require you to go back and redo things.
I agree. I remember in the early, when I started in CALPHAD, people questioned, for example, Mats Hillard, that one should really include the liquid phase because that was not so interesting. But of course, he changed his mind quite early. So you are always shaped by the kind of interest you have, and so you may do it too simple when you start, but you have to improve later on. Yes.
Well, and sometimes you also have time constraints that you need the data now rather than later.
Exactly.
My other question was with the two-state model. I remember we had the discussion at the Ringberg workshop, but ultimately the question was really never fully answered. When you are dealing with the undercooled liquid, eventually you have the glass transition. So how you describe the glassy state? Do you just remove the transitional part from the description, and that gives you the thermodynamics of the glassy state?
No, I would rather suggest that you freeze in the structure you have at the glass transition. So you would have some fraction of atoms doing the translational motion, but they will not change because when you cool further, because that would need more mobility in the liquid phase, in the undercooled liquid.
Well, that's where my idea was coming from.
Yeah.
Because as you cool down, translation will be more inhibited than vibration.
Yeah, but it is inhibited because the structure of the liquid, the structure of the liquid is fixed. So if you could cool further without a glass transition, it would be even more prohibited, of course. So it's like vacancy content in a crystal. When you, at high temperature, you have some equilibrium content, and then when you lower the temperature, the equilibrium content of vacancies will decrease until you need until you reach some temperature where vacancy diffusion is so slow that you do not get any annihilation or vacancy. So I would simply freeze in the structure.
Okay.
Okay, that's great. And let's move to the next question. So let me see, Mustafa, I will promote you to the co-host, but wait a minute. I'm taking advantage as a host here. I have a question to Philip. So thanks a lot for the talk on this Ringberg, on this history of CALPHAD. I have a question on this Ringberg workshop. While I was working on my PhD, I actually, checked the details of some of this Ringberg workshop documents. I was really impressed on that. So, will we keep the tradition to have more this kind of workshop in the future?
I don't know who could answer. I would like that, but someone in Max Planck should be able to answer.
Well, as John says, the Ringberg workshops were organized by Max Planck, originally by the Max Planck Institute for Metals Research, which no longer exists. And then the last one was by Iron Research, so it would be somebody from there who could do the answer. Of course, if you don't want to go to Ringberg, anybody in CALPHAD could organize a workshop like these. the problem, or Ringberg is owned by the Max Planck Society, so it has to be somebody from Max Planck organizing the meeting. But if you go elsewhere, it can be done by anybody.
All right. Okay. That's great. Yeah. Thank you. All right. Okay. So, Mustafa, I already proposed you as a co-host.
Yes.
You can ask your question, or you need me to read your questions.
No, I will ask it. Thank you, sir. First, I would like to thank the teacher for your information. My question, sir, is for someone who want to do the thermodynamic modeling, which using the combination between the
Okay. John, I guess that's a question. It's to you.
sorry, sir, I have the problem in the connection.
So you wonder what is the difference between ab initio calculated values and values obtained by experiments or extracted from experiments? Is that your question?
Yes, sure.
Yeah. Well,
Yes.
that depends very much, and that has been discussed in, for example, the Ringberg workshops, because in some cases the agreement is very good, but there are other cases where it seems to be impossible to combine the ab initio results with experimental information. And then one has realized that, okay, the ab initio results represent unstable structures and so on. So maybe this is something Sequay could comment on. Or Philip, I see you there. Hello, Philip. Good to see you.
My technical capabilities are limited. Yeah.
Thank you very much, sir, for your answer.
All right. Okay, that's great. So the next question will be by Chang Du. I already promote you as a co-host. You can share your video.
Yes. Thanks for the wonderful talk. And actually, I have been reading the two papers John and Professor Liu published quite some years ago in 1989. It's about the calculation of the kinetic interface conditions at a fast migrating austenite and ferrite interface. I don't know if John, you can quickly recall the paper you published in 1989, and so it's about the calculation of a kinetic phase diagram. So it's not the equilibrium phase diagram, and I think I want you to comment on the one of the parameters this model used, the so-called the trans interface mass transfer parameter, the IR parameter, if you remember.
Yes, I remember it quite well. Well, you know, in the model, it is you have the diffusion across an interface is an important parameter, but that is not so easy to measure. You can measure diffusion along interfaces. So we simply had to do some educated guesses, or perhaps even uneducated guesses to find that. But usually what you do is that you vary the parameter until you find best agreement with experimental data. And of course, you can probably, I didn't try it, but probably other people tried it. You can do various type of optimistic simulations, molecular dynamic simulations, or so on to simulate the diffusion across interfaces.
Yeah. And so it's this parameter is closely related to the diffusivity, right? That's
grain
but-
boundary or interface boundary diffusivity. Yes.
yes.
My first
you.
guess would be to take that diffusivity, but then you may realize that okay, it could be different when we go across the interface.
Thank you.
All right. Okay, that's great. So next one is Professor Zikui Liu. You have a question?
All right, it's great. I want to thank Philip and John for the wonderful talk. I like both talks very much. I have two questions, one to Philip. And when I was preparing my opening talk, I asked Philip whether he has any photos of the first meeting, but turned out he said he didn't have it. So yesterday I shared a few photos. One of them was Philip mentioned playing tennis. Oh no, table tennis in the basement. I guess everyone can see the videos. I don't have to share them here. So the question was that where was that meeting that without a window? Was that in Larry's home or in the men's labs?
At Man Labs, can you hear me?
Yeah.
Yes.
Okay. The meeting was at Man Labs, where Larry worked. It was in the town, and the table tennis was in his home.
Okay. So that means that you had 10 people at the first meeting, right?
Yes, about 10.
But not everybody went to Larry's home for that evening.
That's right. That's right. I don't think Claude Lupis or Dick Weiss were at Larry's house. Everybody else.
I think that's very, very nice. And I mentioned yesterday that many families in the United States they have basement. They have a table tennis in the basement. I know you don't have one there too. So
No, I don't have table tennis. You know, need a big house.
Okay. And another thing I really like is that I wrote in the chat is that the history is told by stories. If the histories were told by stories, it's remembered better and be taught better too. I really like the stories Philip mentioned. That's great. As you know, this will be on the website of CALPHAD for the history.
Wonderful.
For the rest of the CALPHAD, the community. And then until, you know, as far as our website is on, it'll be there forever. Thank you very much.
That's good, because my family is curious what I've been wasting my time at for 50 years. So
That's
they
right.
will be able to read something about it at least.
That's right. My question to John was that actually John answered mostly already, is that this extension to other properties. You have two approaches. You have equation of state. Sometimes you have to do that because you, as Ursula mentioned, you need data. You need to get it done sooner. You cannot go back to remodel everything. So that becomes very important. So equation of state. However, if we really want to make the true use of thermodynamics, we want to incorporate them together, make derivatives of Gibbs energy. I think if you go back, as Philip mentioned at the beginning, before the CALPHAD, actually most of them are the equation of states modeling. And it was CALPHAD that really modeled thermodynamics, so to speak, put them into the friend function format and with that stability. And so we built out this huge foundation to enable that. So I hope down the road, all this equation of states will gradually move into the model of Gibbs energy. And not only for thermodynamic problems people typically think about, actually even for people called kinetic parameters, which we believe is thermodynamics. Recently, we work on the Seebeck coefficient. Seebeck coefficient, people always think it's just kinetic properties, but hopefully we demonstrated that it actually is a derivative of the Gibbs energy function. Thank you. John, I hope you agree with me on that.
Yes, I do. And, you know, the Gibbs energy or Helmholtz energy, they are much richer than an equation of state. So they contain much more information. And usually you need at least two equations of state to represent all the information.
Thank you.
Okay. All right. Okay, that's great. So the next one will be the questions from Carmel. And after that will be Susanna. So Carmel, you have your questions?
Hi. You can hear me?
Yes.
Yes.
Okay. Yeah. So I have like two questions. So when you talked about like you can do like precipitation kind of calculations to understand this glass formation. So for those calculations, do we also need interface mobility as input? And how do we usually get like interface mobilities for the processes which is not diffusion control? So that was my first question. And my second question is about the about the nucleation theory. So like, is there any recent advancements in like from the classical nucleation theory for precipitation problems?
Okay. Well, in principle, you need interfacial mobilities, and you certainly need interfacial energies. But in many cases, in many practical cases, it may be good enough to just consider diffusion or transport in the liquid and in the solid phase, but not in the interface. Or it could be approximated as very fast, so very high in interfacial mobility. And your second question, what was your question? Second question?
About the nucleation rate.
Oh yeah,
So,
nucleation, yes. Well, there of course it has been advancement, but it is essentially based on the same old ideas, but it has been extended to multi-component systems and more complex thermodynamics and so on. But the basic assumptions are still the same.
okay. So actually, just one thing I'm not clear about. So what do we usually do for cases where the transformation is not diffusion controlled? If it is interface controlled, so the kinetics will greatly depend on interface mobility. For example, a single component recrystallization, like if you try to predict, it depends on interface mobility. So,
well, in the models we have, the interface mobilities are included or are easily included, but that may not be so interesting from a practical point of view, because when the transformation is concentration invariant or diffusionless, then it's so fast, so it is difficult to avoid crystallization. But in principle, it is not difficult to include it.
thank you.
All right, okay, that's great. So the next one will be Susanna, and after that will be Wei. All right, Susanna.
You are muted.
Yeah, Susanna.
Yeah. Hi, John. Hi, Philip. So nice to see you. So once a CALPHAD, ever a CALPHAD. There is no limit. Yeah, you are there, and it's very good. So, Philip, tell me, if you now would have all the power, all the energy, all the money, what will be your decision for where we should put more effort in CALPHAD?
Wow, what a question. I don't know. If I took all the money, I'd go on a world cruise, I think, instead now, but let me think. Well, I think there is still, personally, despite all advances, a great need for experimental measurement, still. And I would put a lot of money back into the experimental side. There's a lot going on the theoretical side, but the experimental confirmation and provision of data and checking of everything is essential still. So I think that's where I'd put my major effort.
Thank you very much. I love your answer.
Yeah, thank you.
All right, okay, then Wei, you are the next.
Yes, I want to ask you both because you have experienced the development of the CALPHAD approach. So, we have been making a lot of efforts nowadays to improve the lattice stability. So what is your vision about the future once we improve the lattice stability? all the things has to be remodeled. And of course, I know that Zukui would probably also talk about in his lecture about like automated the CALPHAD assessment and so on. Beyond this, what are the expectation or some of the vision that you can tell us? Thank you.
That's a terrible job, redoing the lattice stabilities and then making everything consistent again with all the data that's already been assessed. It's one which is going to happen, but I don't know who's going to undertake it. I don't know what your thoughts on that are, John.
I think it is something that has to be done, and it is already done to some extent within the third generation of CALPHAD. Of course, when one just changed the behavior at low temperatures, it might be that it does not need to be 100% consistent. If you can hope that you can still reproduce high temperature data with such modifications. But I think the only possibility in the future, it is that we make the whole thing automatic. So like in Sequace, SBay and similar approaches. So one can continuously assess or optimize new parameters.
Yeah, thank you.
Of course, machine learning and that kind of stuff that plays an important role there.
All right. Okay. So I think we have time for another 2 questions. Let me have Liang Yan to ask question first, and then we can have Zikui to ask the last question. So Liang Yan, you can open your camera and ask your questions.
Thank you for your presentation. And I'm doing some research about the third generation CALPHAD. So here I have 2 questions. The first one is, can we use a 2-state model to calculate the glass transition temperature? And the second one is, even if now we use more physics-based models to calculate the thermodynamics, could you expect that we can give more reliable predictions at low temperature when compared to the experiments? Because my concern is that at low temperature, the kinetics will matter more than thermodynamics.
Yeah, agree. And of course, there are transformations which do not involve diffusion, like martensitic transformation and so on. And in that case, thermodynamic properties at low temperatures are needed to give the driving forces. And it's interesting, that was where Larry started. He looked at the martensite formation. Yeah. And you had a question about the glass transition, didn't you? Or what was your first question?
The first question is, can we use a 2-state model to...
Yeah, yes. In that paper, which I referred to by Kettner and others, there are expressions for how to represent the diffusion using the 2-state model. And then if you have model, then if you can include that in a crystallization model, then you would you could see when the relaxation of the liquid is no longer possible, and then you could predict the glass transition for various cooling rates. I think it is in principle possible, but as far as I know, it has not been done to that extent yet.
Thank you.
All right. Okay. I think we have time for the last one. So Professor Zikui Liu, you have
Okay, thank you. Thank you. I have those 3 comments and actually those questions too. I really like what Philip's answer about the future experiments are very, very critical, very important. As you can see that we have 4 talks left, 2 of them are experiments, like 50% in the next 4 talks we can have in this conference. So that's extremely important. So we cannot emphasize it enough because everything has to be validated by experiments. So I think that's really, really important. I like that comment. And even though I stopped doing experiments, I stopped doing experiments 20-some years ago, but I believe experiments are very, very critical. That's why I try to work with JC and other people, this one. Yeah. The second about the high throughput, John mentioned that, and Wei mentioned that. I think we'll have to do that because we get more and more data, and also we get more and more knowledge. The ladder stability is really important. We're talking about a 3rd generation or your 5th generation of the ladder stability. Without high throughput, we will not be able to improve them consistently or continuously. So I think that's very important. As you know, that there will be a workshop. There will be a workshop after this conference. I encourage you to sign for that one. It's about a CALPHAD airspace. It's open source. We got support from IBM to cover all the cloud computing expense. IBM is very keen to support that one too. So I think that's the future. So I hope more people will have open CALPHAD. We have few open source codes now. But of course, there's a lot of work. So I hope the community will continue to support that. Of course, this does not diminish the value of the commercial database, commercial codes bring in, because these are the parallel and they support each other, I think. Just like the open database and the encrypted databases, right? Those are 2 different application domains. They're not in contradiction to each other, and they actually complement each other. That's what I think. So the 3rd one is about the machine learning. I saw a question about the machine learning, and also somebody mentioned in the questions too. I think machine learning is the next generation of DFT type of calculations. It can speed up the speed dramatically, and also make us understand it better. Because if you have listened to the machine learning talks people have, it says it's like how we learn, how people learn. Right? You learn from experiments, you learn from DFT calculations, and you learn from the mistakes, and then you improve. So machine learning has to be part of our portfolio for the future of CALPHAD. That's what I'm going to emphasize in my last talk of this CALPHAD meeting. I want to thank these good questions and good answers too by Philip and John. Thank you.
Thank you.
All right. Okay. John. Oh, all right. Okay. So I guess that will be it for today for this Zoom activity. So, we can continue the discussion through this gather town. So with the link, I just paste again there, right? The link and also the passcode. And also regarding the post-conference workshop, I also provide the registration link there. So please also check that. So thank you, everyone. For
can I also add one word?
Yeah. Okay, go ahead.
So yeah, for the gather time, I encourage everyone, to turn on your camera, unmute yourself, and having the communication rather than staying there. Mute yourself. I would not be able to interact. And also, we have the private tables and so on. So that's the best way that you can do the group discussion. Otherwise, if you're standing on the way, people may interrupt you and you cannot hear clearly. Certainly, GetTime is a little bit new to all of us, but I believe, if you get used to, you can actually use it well. It has a function with follow someone and actually also identify someone in the map. So it's very convenient. Just, you move your mouse cursor to people's name and click that button, and you will be able to see these 2 options: follow and locate someone in the map. So it's actually, this way is actually better than the conference on site. Thank you.
All right. Okay. That is great. Yeah. So that's it for today. Yeah. Thank you very much, everyone. So looking forward to see you in next week. Yeah. Thank you. Have a good day.